Welcome back to the MoDyPy Basics tutorial series. If you are the kind of person who rather reads tutorials instead of watching them, hop over to docs.modypy.org, where you'll find this tutorial series in text form. In this tutorial, we will model a DC engine composed of a DC motor and a propeller. I will show you how to use blocks to separate the two parts and to make them reusable, and how to use ports and delegation to connect it all together. Our basic block structure will look like this. We will have a DC motor that accepts some inputs and some outputs, provides some outputs. And we will have a propeller that also accepts inputs and provides outputs. The DC motor will be a stateful block, so it does have internal state, and the propeller will be a stateless block, so it simply translates the inputs into outputs without any memory. And our third block will be the engine that encapsulates all of them together and connects them up in a sensible way. So these are our three blocks. But we will also need some additional elements. We will need so-called ports. Ports are like signals that are placeholders. So a port can stand in for a signal, but it doesn't deliver a value by itself. It first has to be connected to a signal. And the reason why we need ports is to solve cyclic dependencies. So for example, our DC motor will need some input that is generated by the propeller, namely the drag torque. On the other hand side, our DC motor will produce an output that is required by the propeller as input, namely the speed of the axle. And we wouldn't be able to create either of these if we had to have the signals available before creating the blocks. So instead, we use ports for these input elements. They are stand-ins for the signals. And once we have created the DC motor and the propeller, we can connect up the respective source signals to these ports. And we can then use the ports just as a signal, as if it was the input signal itself, and it will deliver the value that is provided by that signal. And in the first part, we will model a DC motor block. I won't go very much into detail about the theory of the DC motor block, but suffice it to say, we have as input the voltage across the terminals, and we have some external load torque, which later on will be the aerodynamic drag produced by our propeller turning in a fluid or a gas. We will need some parameters. There's the internal resistance, the internal inductance of the coil, and we will have the so-called motor constant, which gives us both the voltage induced by the motor coil due to turning at a specific velocity, and it will give us the constant for calculating the torque generated by the motor based on the current. And we have these two equations for the change of current through the coil and the change of angular velocity of our axle. So here, this is the input voltage, this is the voltage drop on the resistor, and this is the induced voltage on the motor coil. This difference here is the voltage on the internal inductance, and if we divide it by the inductance, we get the derivative of the current. And similarly, here we can calculate the torque generated by the coil in the magnetic field due to the current flowing through it. And we subtract the drag torque or load torque from it and divide it by the moment of inertia to get angular acceleration. So this block is what we want to code up in the first part of this three-part tutorial. And I have already prepared parts of the code here. First of all, I have imported our classic system and state classes, and we will also need the block class to define our DC motor block. I also imported everything we need for simulation and for plotting. And here I defined some parameters for one motor that we want to simulate. Let's define our DC motor block. For that we define a class, and we call it DC motor, and it inherits from the block class. The block class is the base class for all blocks in MoDyPy. It has some very simple functionality. First of all, we need to specify a parent for our DC motor. So some object that will contain our DC motor. That can either be the system or some other block. Then we will declare parameters for our constants. So we have the motor constant, we have the resistance, we have the inductance, and we have the moment of inertia. And we will also declare the initial values of our states. So the initial current, which we will set to none, the default, and the initial speed, our angular velocity, which we'll also set to the default none. Now let's call the super constructor, the constructor of the block class, and just pass it the parent element. We need to store our parameters. So that we can refer to them later when we calculate the derivative of current and angular velocity. We will have two states. One is the current, and we declare those two states as properties of our block so that we can access them. So here the owner is the block that we're declaring, so it's ourselves, the DC motor block. We have a derivative function, and for that we will use a bound method of the object. So we'll say self current dt. This is a bound function, so it knows the object that it is being called on and can thus access any properties of that object. And we will set the initial condition to the initial current. Note that this is a scalar state, so we don't specify any shape because the default shape is for scalar states. We also have the state omega, which is our rotational or angular velocity. Again, the owner is the object itself. We have the derivative function, which we will call omega dt, and we have the initial condition, which is initial omega from the parameters. Now we need to declare our input ports. We have two input ports. One is the voltage, and for that we will need the port class from the MoDyPy model package. So I will add that here as well. And that port is, as I said, simply a placeholder. You can also specify a shape here so that the port can only be connected to signals of that shape. But as the default shape is for scalar ports, we simply use that. And the other input is the external torque that will come from our external load, in our case, the propeller. So that's actually it for the interface. We have our parameters, we have our states, and we have our input ports. Now let's define our derivative functions. So we will define object methods that accept, of course, the object itself and the system state. And we will simply calculate the derivative of the current, and that is the voltage minus the voltage on the resistor I'll write it differently, I'll write it this way, minus the voltage induced by turning the coil and all of that divided by the inductance. We do the same for the derivative of the angular velocity. Here we have the torque generated by the coil. And we subtract the external torque. And all of that needs to be divided by the moment of inertia. And now we need to define two additional signals, or we want to define them. Note that states and that states themselves can be used as signals automatically. So we already have the two outputs for the angular velocity and for the current here. But our block diagram says we also want the speed in revolutions per second, and we want the torque generated by the motor as output. So we define a function or method named speed RPS for speed revolutions per second, and have it simply return the speed, so the angular velocity, divided by 2 times pi. And we need to import NumPy here to access that pi constant. And to make that a signal, we need to add the signal method decorator, which we also import from the MoDyPy model package. That decorator is similar to the signal function decorator in that it accepts the same arguments, the same parameters, but it works on methods instead of functions. And the distinction is important. So we have another signal method, and that is the torque. And the torque is simply the motor constant multiplied by the current. And with that, our block is completely defined. We have our states, we have our external ports for the inputs, we have our derivative functions, and we have the signals that we want to use. Now we can define a little system containing just this DC motor. We declare a system and we create our DC motor. It is part of our system. And now we need to have the parameters set. And we will keep it that way. We will keep the states at their standard initial values. So now we can try simulating that. Simulator, creating a simulator. And we'll set the maximum step size a little bit lower than we had before, because the motor will be moving quite fast. We will get our result here. And we will have it run just for 1 second. And then we will plot this. We will plot the speed in revolutions per second over time. And now if we run this, we get an exception, PortNotConnectedError. And we see that it's been using the voltage port here. And as I said, the ports are simply placeholders. They stand in for signals, but they need to be connected to signals. So we need to define signals to provide values for the voltage and the external torque. And for that, we need the constant port or the constant signal. We can take that from the blocks sources library. There we have the constant function, and it allows us to declare a signal that will provide a constant value. We will set that to 1.5 volts. And we will also need a torque, but we will set that to 0 because right now we don't have any load. That would be Newton meters, by the way. Okay, now we need to connect them. So we say voltage, connect, DC motor voltage. So that means that we want to connect the DC motor voltage to this constant source. And we connect the torque to the DC motor external torque. By the way, you can switch these. So the connect function is defined in a way that the order of these parameters does not matter. What will happen if you connect a port to two different signals is an exception will be thrown as well. So now we have all of that connected and we can run it again. And we get a nice run up of a motor to about 290 revolutions per second. That probably would be too fast for this kind of motor, but that is because there is no load yet. So we defined our first block here. And in the next step of this tutorial, we will define the propeller block.